In this video, we are going to be taking a look at NJC 2021 JC2 Prelim papers. We will be taking a look at the first few questions, and in the next video, we are going to be looking at the next few. So we are going to be spending some time to look at the first half of this paper, and then we are going to complete it in the next video. So in question number 1 over here, we have in part 1 a trigonometric identity proving question. I'm going to start with the left-hand side. So for part 1 over here on the left-hand side, we have this. We have a sine of m plus 1 theta minus n theta. This is going to be divided by the denominator, which is going to be cosine n theta cosine m plus 1 theta. So in order for me to prove this in the numerator, I'm going to make use of the trigonometric identities that is available to me in my MF26. So let's take a look at MF26. In MF26, okay, let's see which trigonometric identity we can be making use of. We have a sine A minus B. So I'm going to be making use of this. Sine A minus B is equal to sine A cosine B minus cosine A sine B. So for the numerator, let's try to rewrite this. It is going to be sine m plus 1 theta cosine n theta minus away cosine of the first angle, which is this. Then sine of the second angle, which is this. This is going to be divided by the same denominator, cosine n theta cosine m plus 1 theta. Let me rewrite this further by breaking up this this expression into two fractions. So this over this, we will have a sine m plus 1 theta cosine n theta over this, which is cosine n theta cosine m plus 1 theta. Minus away, I'm going to do the same thing for the other part of the numerator, which is going to be cosine n plus 1 theta sine n theta. This is going to be divided by cosine n theta cosine n plus 1 theta. So if I were to look at what we have so far, we can see that cosine n theta can be cancelled over here, and cosine n plus 1 theta and cosine n plus 1 theta can be cancelled over here, which will leave us with a sine n plus 1 theta over cosine n plus 1 theta, and that will give us a tangent. So this is going to be tangent of n plus 1 theta, which is already part of what the question wants us to show. Then sine n theta divided by cosine n theta gives us a tangent n theta. Okay, so this is what we're supposed to show according to the question. Next, part 2. Part 2, hence, so we're going to be making use of this result. Hence, find in terms of n and theta an expression for this series where n are all positive numbers. So let's take a look at this series. Let me rewrite it first. We have a secant theta, secant 2 theta, then plus secant 2 theta, followed by a secant 3 theta, then a secant 3 theta, secant 4 theta, and all the way until the very last term, which is secant n theta and secant m plus 1 theta. So looking at what we have here, of course I see some pattern, like 1, 2, 2, 3, 3, 4, and so on. But what I think we can do is to try to consolidate this entire series into a more summarized form. What is a more summarized form? For example, using the sigma notation. I think that is a good way for us to re-express this. So if I were to re-express this into the sigma notation form, then it should be summation of, this is like if r, okay, I'm going to let r be equal to 1, and I'll look at this as if it is a secant r theta. Then this will be a secant r plus 1 theta. So if I were to do this, the very last r will be this, which is going to be n. And then after that, r plus 1 will become n plus 1. So I'll go all the way until here for me to try to express re-express this series into a more condensed form. And I think I can actually try to find a way to make use of the previous part, because what is a secant? Secant is 1 over cosine. So what we have here is going to be a summation from r starting from 1 to n of 1 over cosine r theta and a cosine r plus 1 theta. And we do have a trigonometric identity that looks sort of like this, which is here, right? 1 over cosine n theta, cosine n plus 1 theta. But I guess the numerator is sort of like a pain, unless you can see something about the numerator. Okay, there's this small little trick that is in the numerator, which is more like an algebraic trick, which is n plus 1 theta minus n theta is n is no, it is just theta, right? Sine n plus 1 theta minus n theta is just going to be sine theta, which means that the trigonometric identity that we have over here is actually just simply going to be a sine theta in the numerator divided by the denominator, which is cosine. I'm going to replace all the n by r. Okay, so r theta cosine, this is going to be r plus 1 theta. This will be equal to, we have this as a tangent r plus 1 theta minus tangent r theta, which means that 1 over r cosine theta cosine r plus 1 theta can be written as, let me try, okay? So sum from r is equal to 1 to n. I can rewrite this by dividing sine across to the other side. Then it will become a tangent r plus 1 theta minus tangent r theta divided by sine theta. Okay, because when we try to simplify this entire expression here is actually just theta, which is here. So now we have a theta, but there's no r. So this, I'm going to just factorize it out of the sigma notation, which will be giving us this. Okay, let me write it down here. So this will be giving us a 1 over sine theta. Then we will be summing from 1 all the way until n of tangent r plus 1 theta minus tangent r theta. And what I'm going to do is I'm going to expand this and using the method of difference presentation. So I guess that is the way that we can be condensing this and evaluating this summation. So this is going to be 1 over sine theta multiplied by, when r is equal to 1, we have a tangent 2 theta minus away tangent 1 times theta. Then after that we have a tangent 3 theta minus away tangent 2 theta, and then tangent 4 theta minus tangent 3 theta. I can see terms being cancelled out, and the cancellation follows a particular pattern. 2 rows gives me 1 cancellation, so I'm going to write down the last 2 rows. That will be when r is equal to n minus 1, which means that we will have a tangent n theta minus tangent of n minus 1 theta plus tangent n plus 1 theta minus tangent n theta. So we are seeing the pattern of cancellation appearing in this way, and we verify it using a more general 2 terms, 2 consecutive rows, which is going to be this. So we know that in between here, they will all disappear because we have recognized this as our pattern. So my final answer is 1 over sine theta multiplied by whatever that is left. Whatever that is left is going to be here, tangent n plus 1 theta minus this, which is tangent theta. Okay, this is for question number 1. Let's continue. Let's take a look at question number 2. Okay, a slightly long question. Okay, in question number 2, the number of bacteria in millions. I think this is an important piece of information that we need to take note of, because subsequently the question says that in this, there's this number of bacteria in million in culture A at the start of the nth day is denoted by UN. So please take note, UN is in millions, okay, for n to be all positive integer. After the start of a day, a researcher subjects the culture A to high temperatures that kill 60% of the existing bacteria, which means that 40% is going to be left. At the end of the day, 3 million new bacteria are produced in culture A, and there are 5 million bacteria at the start of the first day, which means that U1 is equal to 5. Part 1. In part 1, we are supposed to write down a sequence in the form of UN plus 1 is equal to AUN plus B. This is a recurrence relationship where the relationship is trying to describe to us how one term is going to be related to the previous term or the previous few terms. So now we are supposed to verify that UN plus 1 is going to be related to the previous term, UN, in this way. And according to what the question says, the next day, okay, which is going to be dependent on the previous day. In the previous day, which is the nth day, 60% of the bacteria, 60% of the existing bacteria is going to be killed by the high temperature. So on the previous day, if it started off as UN, then 60% is going to be killed, so I'm going to be having 40% left. And according to what the question says, 3 million new bacteria are going to be produced in culture A. And because UN plus 1, they are going to be in millions. So here, I'm going to add in a 3 million, which is actually going to be written as 3. So this will be my answer for part 1. Okay, this is just a 1-mark question. Something that I am not very sure about is actually part 2, not about the answer, but it is about the length of my solution, because this is a 1-mark question, and as I take a look at how NJC present it in their solution, they actually use a feature that is in the graphing calculator, but it is not exactly taught in H2 math syllabus. So I'm a little bit like, okay, because that is about using your calculator, switching the mode from function, parametric, switching the mode to sequence. Okay, but we don't really learn that in our H2 math. So I'm not entirely sure about their solution, okay, whether it is relevant to our H2 math. So I'm going to use my own method to try to find out what is the behavior of the number of bacteria in culture A in the long run. My solution is going to be long, okay? I cannot justify it for the 1 mark that is given. So according to the question, we have this. This is the relationship. And we also know that U1 here is equal to 5. That's what the question says, because 5 million bacteria is going to be produced at the start of the day. So U1, that is going to be equal to 5. Which means if I were to make use of this recurrence relationship, U2 is going to be equal to 0.4 of U1, then plus 3, all right? We have this. And in fact, we can do the same thing for U3. U3 will be 0.4 of U2 plus 3. And what if we were to try to substitute this into here? Because this is not an unknown, U1 is equal to 5. So we can in fact substitute 5 into U1 and get a number for it. But before we substitute it in, I'm going to try to see whether I can see any pattern, because I can't possibly keep substituting and then try to look at the numbers in the long run. So I'm going to try to do it in a more general form first. So this will be 0.4 multiplied by U2. I'm going to replace it by this expression here, which is going to be U4 times U1 plus 3. Okay, I am not substituting U1 as 5 into here and evaluating it first, okay? Because if I were to do this, I may not be able to see a pattern. And that will mean that I really have to do a substitution all the way until infinity, okay? And that's not what I plan to do. So this that I have here is going to be 0.4 square of U1 plus 3 times of 0.4. Okay, we have this, and let's see what is U4. U4 is going to be using this recurrence relationship again. U4 is going to be 0.4 times U3 plus 3, which is going to be equal to 0.4 times U3, which is this. So multiply by this, which is 0.4 square U1 plus 3 times of 0.4. Then let's not forget about the plus 3. So we have a plus 3 here. This is going to be equal to 0.4 times 0.4 square, 0.4 to the power of 3, then U1. I'm going to write this 3 first. So we have 3, then after that, we have this, which is going to be equal to 3 times 0.4. Oops, I've made a mistake. So it should be this U2, then there should be a plus 3. Let me correct my mistake here. So this over here is going to be 0.4 times U2, this plus 3, then I've forgotten this plus 3. So plus 3, so this is going to be equal to 0.4 square of U1 plus 3, then plus this times this, which is going to be 3 times of 0.4. Let me add it in here, okay, to redeem myself. So we have this over here, 0.3. Okay, I'm going to erase this too. So we have 3 plus 3 times of 0.4, and this time I'm not going to forget about this 3, so plus 3. So this is going to be equal to 0.4 times 0.4 squared, 0.4 to the power 3 U1 plus, I'm going to write this first, so it's going to be 3. This times this is going to be 3 times of 0.4. This times this is going to be 3 times of 0.4 square. In fact, I am already seeing a pattern. Okay, here it seems like it's going to become a GP. Okay, I can probably stop here and make a prediction for UN. Okay, if it is not sufficient for us to see a pattern, maybe it will be all right to just write down a U5. But of course, for 1 mark question, we are really writing too much over here, okay? So UN, let's try to see what pattern we are seeing, okay? So if it is 2, then we have a U1, 0.4 to the power of 1. If it is 3, we have a U1, 0.4 to the power of 2. So 2 power 1, 3, 0.4 power 2, 4, we can see that it is going to be power 3. So n here, it will be 0.4 to the power of n minus 1 U1. So this is the pattern that I'm seeing. And then it is going to be a sum of a GP. And if it is U2, 1 term, 3, 2 terms, 4, 3 terms, and that will be n number of terms. With the first term as 3, and the common ratio is 0.4, the number of terms is n minus 1 number of terms. We have this divided by 1 minus 0.4. So what we have now here is going to be 0.4 to the power of n minus 1. In fact, we can actually probably substitute U1 in already. I'm going to substitute and replace U1 by 5 over here. Then plus 3 divided by 1 minus 0.4 is actually going to be 5. 5 of 1 minus 0.4 to the power of n minus 1. And now I guess I can start to discuss about what is going to be happening in the long run. Long run as in like we are going to let n goes to infinity, okay, to infinite number of days later, what is going to be happening. So when n tends to infinity, un will tend to this 0.4 to the power of infinity will become 0 plus 5 times of 1 minus 0.4 to the power of infinity will also becomes 0. So this will become 5. So this is going to give me my answer. In the long run, the number of bacteria will be tending towards 5 millions. Okay, this is for part 2. I need some space, so I'm going to erase this and to continue with the next part, part 3 of the question. So in part 3 of this question, we are looking at culture B, and the number of bacteria is going to be continued to be recorded in millions. And this time, for the nth day, the number of bacteria is going to be Vn. And it is given to us that for Vn is equal to Pn divided by, it is the same n, Pn divided by n squared plus Qn plus R. And the researchers started the experiment for culture B on the first day, which is the 1st of April, and collected the following data. So at the start of 1st of April, which is the first day, that is when n is equal to 1. That is when n is equal to 1. So for part 3, I have my first piece of information, which is V1 is given to me as 2. On the 2nd of April, that will be V2. My second piece of information will be V2 is equal to 2.4. And on the 4th day, 4th of April, that is V4. V4 is given to me as 1.6. I'm going to make use of these 3 pieces of information to solve for PQR. This has been transformed into a system of linear equation question. So V1 is equal to this, which means that we are going to be having a P times of 1 divided by 1 square plus Q times of 1 plus R. This is equal to 2. So it is going to be P is equal to 2 plus 2Q plus R. So we have a P minus 2Q minus R. This is equal to 2. This forms for us our first linear equation. For the second equation, it is going to be coming from here. It is when n is equal to 2. So it is going to be P times of 2 divided by 2 square plus Q times of 2 plus R. This is equal to 2.4. Cross multiplying, we have 2P is going to be equal to 9.6 plus 4.8Q plus 2.4R. And I'm going to bring everything over to the left-hand side. I'm also going to, by convenience, divide throughout by 2 because there's a common multiple here, which is 2 common. Yeah, so if I were to bring everything over to one side and dividing it throughout by 2, I will be getting a P minus away 2.4Q minus 1.2R. This is equal to 4.8. This forms for me equation number 2. As for V4, that is when n is equal to 4. So it is going to be P times of 4 divided by 4 square plus Q times 4 plus R. This is equal to 1.6. So we have a 4P is going to be equal to, cross multiplying this, it is going to be equal to 25.6 plus 6.4Q plus 1.6R. Bring everything over to one side and dividing throughout by 4 gives me this P minus 1.6Q minus 0.4R. This is equal to 6.4. This forms for me my third equation, and I can then press all the 3 equations into my graphing calculator to solve for PQR. I'll be getting P to be equal to 6, Q is going to be equal to minus 1, and R is going to be equal to 3. And in part 4 of the question, we are supposed to state the date when the researcher is going to be recording the number of bacteria in culture B to be below 500,000, which means that we are expecting Vn to fall below 0.5, 500,000, and Vn is in terms of million. So we're expecting Vn to fall below 0.5. For PQR that we have found, we can now rewrite Vn. Vn is going to be equal to 6P over n squared minus n plus R, which is 3. And in order for me to analyze which day this entire thing is going to be fall below 0.5, I'm going to press this into my calculator, and then I'm going to generate a table, letting the calculator substitute different values of n into this expression here. And if I were to look at the table from my calculator, when I look at n and I look at Vn, when my calculator substitute 12, the 12th day, Vn from my calculator will be giving me a 0.5333. It is still going to be above 500,000, but on the 13th day, this is going to be equal to 0.4906. This is the first day when the number of bacteria recorded is going to be less than 0.5, and subsequently, let's take a look at what we have in our calculator. From the calculator, this is 0.4541. So based on this, I know things happen on the 13th day. So on which date will the researcher first record the number of bacteria in the culture B to be below 500,000? We will be seeing this happening on the 13th of April. Okay, let's take a look at question number 3. Okay, the next question, question number 3, we have a graphical transformation question. We started off with this graph, and we are supposed to come out with a transformation that will be giving us the graph of y is equal to 1 over fx for part 1. So let's try to sketch this based on what we have been talking about on Achevas TV. We can try to sketch this based on what we have memorized about certain features, although it is definitely possible for us to analyze and assign some meaning and understanding to those things. But for for the sake of the exam, I think it is good to memorize some of the features. Then after that, we're going to analyze the rest of the parts of the graph. So for our analysis, for our memorization features, we are going to look at the asymptotes, and we're going to be looking at all the xy intercepts. So for asymptote-wise, vertical asymptote is going to become a x-intercept. So this x is equal to 2 over 3 is going to become an x-intercept, and the x-intercept is going to be, let's say, somewhere here. And this point, I'm going to go for a point 2 over 3 and 0. That is transformed from this. Horizontal asymptote y is equal to minus 2 will become a horizontal asymptote y is equal to minus 1 over 2. So I will draw a horizontal asymptote for this part here. This is going to be y is equal to minus 1 over 2. So I've worked on the two asymptotes that are given to me. I'm going to next work on all the xy intercept. There are only 3 that I can see so far. It is going to be here, here, and here. So x-intercepts are going to be giving us vertical asymptote. Oops, that means 1 point here. This point here is when x is equal to 1. So x-intercept is going to be giving us vertical asymptotes. So minus 4, okay, let me sketch it out. Minus 4, x is equal to minus 4 will give us our first vertical asymptote. That will be, let's say, somewhere here. Okay, this will be our vertical asymptote. This is going to be x is equal to negative 4. We have another vertical asymptote from the original x is equal to 0. As an x-intercept, it will become a vertical asymptote, and that is going to be x is equal to 0. One more, that is here, when x is equal to 1, it is going to give us our vertical asymptote, and I'm going to be sketching it down here. Okay, so this will give us the vertical asymptote x is equal to 1. We have analyzed all the xy intercept, which we have sort of like memorized. We have analyzed all the asymptotes, which we have also sort of like memorized the features when it is being transformed to the graph of y is equal to 1 over fx. And next, let's try to do an analysis from the left all the way to the right. And our analysis depends on one very, very simple thing, which is actually according to what the question wants us to do, which is just simply conveyed to us via the labeling of the graph that we will be doing subsequently. Because on this graph, it is going to be labeled as y is equal to 1 over fx. So basically, all the y coordinates here represents 1 over the original fx, which can be found on the y coordinate on this graph. Which means that, for example, for a point that is like this, minus 1, 5 over 2 will become a point minus 1, 2 over 5. Let me just do a quick tabulation here. So minus 1, 5 over 2, this will become a point minus 1, 2 over 5 on the graph of y is equal to 1 over fx. And this makes the transformation very, very easy, because as long as I can have a coordinate of a point that is here, I will be able to transform that coordinate by doing a reciprocal to the y coordinate to a point that is here. But sadly, we don't have the coordinate that is here. But the good news is we can guess, we can come up with an arbitrary number to assign to a point that is going to be given to here. So for example, if I were to go for a point that is, let's say, all the way to the left here, I'm going to assign an arbitrary coordinate to it. All the way to the left is going to be minus 100. And the y coordinate is like minus 100 also. Doing a reciprocal to the corresponding y coordinate, it is going to be minus 100 and negative 0.01. So I'm going to put a point that sort of like represents the transformed version of this point that is here. And that point will be somewhere here, very, very close to the horizontal x-axis. And then it is going to slowly go towards minus 4, which is going to be a vertical asymptote here. So since it's going towards minus 4, just before minus 4 happens, I want to know what is the behavior that is happening on this particular graph, the reciprocal graph. So I'm going to assign an arbitrary coordinate to it also. For example, the x coordinate, because it is just to the left-hand side of minus 4, it can be negative 4.1. And the y coordinate is negative 0.00, okay, negative 0.1, that's too much. So negative 0.1, okay, it's not too much, it's just that I think negative 0.1 is good enough. So anyway, this point here will become negative 4.1, and this will become negative 100, which means that if I were to poke a point that represents this, which is a transformed version of a point that is somewhere here, it is going to be here. Okay, somewhere over here. So if I were to join these 2 points together, I will get a graph that looks something like this. Right? This will tell me that although the graph will tend towards the horizontal x-axis, but you will never actually touch the x-axis because you'll just become more and more negative, more and more negative. It will just go more and more close to the x-axis, but you'll never ever actually touch the x-axis. This is the behavior of a horizontal asymptote. I'm going to quote it. The horizontal asymptote here is y is equal to 0. So I have a new asymptote, y is equal to 0. Let's continue. Let's continue with a point that is maybe slightly to the right-hand side of -4. I'm going to call it -3.9, and the y-coordinate will be positive 0.01, which will be transformed to -3.9 and let's say 100. So -3.9 and 100, it is going to be somewhere here. Then after that, the next point is going to be at, say, here. Okay, -1 and 2/5, which is what we have already transformed here. So it is going to be from here coming down all the way until this point over here. And then as it moves closer and closer to 0, are you able to imagine this already without writing this? Let's try. So as we go nearer and nearer to 0 here, the x is, let's say, -0.1. Then the y is 0.01. 1 over 0.01 is going to be positive 100. Positive 100. So we have a -0.1 and a positive 100. That point is going to be somewhere here. So from here, I'm going to just join it over to this point here. The same goes for this point. The y-coordinate is -0.01. -0.0. Okay, -0.01 will become -100. So -100 is going to be here. It's going to be joined to a point that we have already predestined it to pass through, which is the point 2/3, 0. Then as it progresses towards 1, this point here, the y-coordinate is 0.01, it will become 100. So 100 is going to be, let's say, here. So from here, it is going to continue up, joining to here. Then for this point that is here, the y-coordinate can be -0.01. 1 over -0.01 is going to be -100. So it's going to be somewhere here. A point that is here, the y-coordinate can be like -1.9. And here it is going to be a value that is going to be even smaller than -0.5. So it's going to be somewhere here. So from here, we're going to join to this point that is here. So this will give us the graph of y is equal to 1 over fx. And the next part requires us to sketch the graph of y is equal to f prime x. So for part 2, we are going to be sketching the y coordinates that is on this graph to represent the gradient that we are seeing there. So f prime x. I'm going to also make use of a lot of analysis in order for me to sketch this graph. And process-wise, we don't really need a process, but I'm going to still stick to a rough process that I've described on the Achevas TV. So if I were to stick to that, the first thing that I'm going to try to do is to look at all the points where f prime x is equal to 0. The gradient that is on this graph is equal to 0. For example, I have a point that is here, I have a point that is here. These are 2 points when f prime x is equal to 0. And which means that if f prime x is equal to 0 on this graph, the y coordinates that is corresponding to these 2 points are also going to be equal to 0, right? So we have one point that is, let's say, here. Okay, this will correspond to this point where the gradient is 0. So we have a -4, 0 here. We have another point which is at x is equal to -1. The gradient is also going to be equal to 0. So let's say it is a point here. So this point will be -1. Y, which represents the gradient, is 0. Then the next thing that I will do is I'm going to take a look at what we have here, and I'm going to work on all the asymptotes. In fact, I should be working on the asymptotes first. So if I were to work on the asymptotes, vertical asymptote will remain as vertical asymptote, because at vertical asymptote, the gradient is undefined on here. Okay, so when x is equal to 2/3, the y, which represents the gradient, will also be undefined. So I should have a vertical asymptote here. Let me sketch it out. So we have this. This is x is equal to 2/3. And for horizontal asymptote, I can see that the gradient here is equal to 0. So horizontal asymptote that is on the graph of y is equal to fx will become a horizontal asymptote of y is equal to 0, which represents the gradient. The gradient is 0. So we have this. So I should have started off with the asymptotes first, which I didn't, but now I'm going to do it first. Then after that, I'll look at the points where f prime x is equal to 0, which is these 2 points here, if I'm going to be following the strategy that I've discussed on Achevas TV. And the next step is to look at, like in general, okay, whether we are looking at parts of the graph that are of positive gradients or negative gradients, because that will tell us where the y coordinate is going to be, whether I'm going to be working on positive y coordinates or negative y coordinates. For example, all the way to the left of -4, the gradients are all positive, which means that we are going to be expecting the y coordinates to be all positive. My graph must be somewhere here, above the x-axis. Then from -4 all the way until -1, it is still going to be a positive gradient, which means that my graph will still remain as here, the part that is above the y-axis. But from -1 onwards all the way until 2/3, the gradients become negative. So from -1 all the way until 2/3, my graph is going to be below. So I will be expecting myself to be sketching it here. And then from 2/3 onwards, the gradients are all negative, which means that from 2/3 onwards, the y coordinates are all going to be negative. I'll be expecting my graph to be occupying this part of the Cartesian plane. So based on this, okay, this as my rough gauge, I'm going to go for my last step, which is the analysis. Okay, I think the analysis is the most important one. So let's do a good analysis of what that is happening by trying to focus on the gradient that I'm seeing here. So all the way to the left, we have a pretty big positive gradient, and the gradient will slowly go to 0. Still positive, but it will slowly go to 0. So I'm going to have a positive y coordinate here because it represents the gradient I'm seeing there. So the gradient will be positive, y coordinate here will be positive, and it will become less and less positive all the way to 0. It will become less and less positive all the way to 0. Then it will become positive again, and it will become more and more positive. So it will just become positive y coordinate again. It will become more and more positive. And at some point, which I cannot determine from the information that is given to me by the question, at some point it's going to become less and less positive, but still positive, then you will go to 0. So at some point, the y coordinate will start to fall, still positive, but less and less positive, back to 0 at x is equal to -1. Then after that, the gradient will become negative. So the gradient will become negative means the y coordinate will start to become negative. It will just become more and more and more negative as it goes towards x is equal to 2/3. So I've already ticked here, so I'm going to be expecting my graph to be here anyway. So the y coordinate will become more and more negative as it tends towards x is equal to 2/3. And to the right of 2/3, the gradient is still very, very negative. The y coordinate is still going to be very, very negative. And it will slowly become less and less negative, then back to 0. So it will become less and less negative, and it will slowly tend towards 0, which is our horizontal asymptote over here. And this will represent for us the graph of y is equal to f prime x. Okay, done for part 3. Let's continue with the next part of the question. The next part of the paper. It is an integration question. Let's take a look at this. So question number 4, part 1. We are supposed to start off with a differentiation. So let's try to do this simple differentiation. We are supposed to be differentiating e to the power of cosine 2x. So I'm going to be making use of chain rule. That will give me a e to the power of cosine 2x. Differentiating cosine 2x gives me a -2 sine 2x. Let me just rewrite this. It is a -2 e to the power of cosine 2x. Then we have a sine 2x here. And in part 2 requires us to integrate e to the power of cosine 2x sine 4x. And to integrate this, let's make use of experiences that we have when it comes to practicing integration question for exams. We know that for a question that is like this, I'll definitely be making use of the previous part. How can I be making use of the previous part? First of all, we have a differentiation, which means we also have a integration result that is from the previous part. So based on this that we have here, we know that if we were to be integrating -2 e to the power of cosine 2x sine 2x. This will be giving me e to the power of cosine 2x plus c. Okay, so we have two results that are from the previous part. Are we able to immediately use it here? I don't think so, because we have e to the power of cosine 2x, but we don't have a sine 2x. We don't have a minus 2. So in order for us to do that, let's revisit what we have in our MF26 in our formula sheet. And we are going to make use of this, which can help us to convert 4x to 2x. So what I'm going to try to do is to rewrite this as integration of e to the power of cosine 2x. Then this will become 2 sine 2x cosine 2x. Okay, now we have this. And I think what I'm going to try to do is to try to do an integration by parts. So to do an integration by parts based on, I'm deciding this based on the information that I have previously, okay, because I know I can be integrating this. I can be integrating a part of what we have from the previous part. So just to make sure that I can use this result directly, I'm going to regroup this, and I want to try to introduce a negative to this. So I'm going to put a negative outside. So this will be integration from minus 2. Okay, 2 is from here. Then e to the power of cosine 2x. I'm going to group this sine 2x together with this. So this will be a term. Then after that, the other one is going to be cosine 2x. Okay, I think now I am ready to try doing an integration by parts. And I'm choosing u and dv dx based on the result that I have previously, because I know how to integrate this. So I'm going to let u be this expression here. I'm going to be letting u be equal to cosine 2x, while letting dv dx be equal to negative 2 e to the power of cosine 2x sine 2x. So based on this, du dx is going to be minus 2 sine 2x, and v, using the previous part, will just be e to the power of cosine 2x. And now I'm going to apply integration by parts to this, which is going to be equal to negative of integration by parts. Okay, so let me put out an overall bracket. It is going to be uv. So we will have e to the power of cosine 2x. Then after that, cosine 2x minus integration of v du dx. This multiplied by this. So it is going to be minus of this times this. Hey, guess what? This times this actually gives me exactly this, right? So it is going to be minus 2e to the power of cosine 2x sine 2x. Okay, this is going to be simple because we already know how to integrate this, and that is going to be based on part 1 for this. So for what we have here, it is going to be a negative of e to the power of cosine 2x minus the result of this is just simply going to be e to the power of cosine 2x. So we have this plus c. I think I'm going to just factorize out e to the power of cosine 2x, and maybe the negative, I'm going to just pump it back into the bracket to make this look a little bit sort of like nicer. So factorizing out e to the power of cosine 2x gives me this. Negative 1, if I were to put it inside, I will have a positive 1, then minus this. So it will be a 1 minus cosine 2x, then plus c. This will be my answer for part 2. And we have a part 3. Oh, part 3, then they say hence. Okay, in fact, part 2, we have already made use of the previous part. But part 3, it is also a hence question. And for part 3, let's take a look at it. Part 3, we are supposed to integrate this expression here. Okay, part 3, let me just write it down. Part 3, we are supposed to integrate e to the power of cosine 2x. Then after that, cosine 3x sine x. Okay, we are supposed to be integrating this. And once again, we are not able to proceed because we don't have something that looks similar to this, neither is this looking that similar to this that we have, or the differentiation that we have. And I'm going to go back to my MF26. I'm going to go back to my formula sheet to see which trigonometric identity which I may be able to make use of. so that I can convert this to make it look something that is a bit more similar to the previous part. And I think I'm going to find my answer here. Okay, in fact, we have a cosine, then followed by a sine. Cosine, then followed by a sine. So I'm going to make use of this. But in order for me to convert this, okay, let's just do a quick practice, okay, of how I can be making use of this. But instead of going from the left to the right, we are going to come up with our own version to go from the right to the left. Okay, because this is actually obviously the right-hand side of this second trigonometric identity over here. Let me just write this down first. So for the identity that we have, it is actually a sine p, then after that minus sine q. This is equal to 2 cosine half p plus q, then sine half p minus q. It is actually very simple to convert from the right-hand side here to the left-hand side so that I can be applying this to what we have here. Of course, we need a 2 here, and that is not difficult. So for that, I'm going to just add a half outside so that I can introduce a 2 to this. 2 cosine 3x sine x. Okay, which is this 2 over here. But how about this? This is just one term. Okay, but now we have like 2 terms over here. So if I were to look at this over here as A, angle A, and this over here as angle B, are you able to like use a bit of mental sum and see that A plus B, which is half P plus Q, plus half P minus Q, the Q will disappear, you left me with just a P, which is this. Okay, that means this that is over here is in fact just simply A plus B. Similarly, if I were to take A minus B, this minus away this, I'll be left with a Q. So this Q over here is simply A minus B, which means I can now convert this into a sine A plus B minus sine A minus B is equal to 2 cosine A, then sine B. Okay, so now we have another identity that I can be making use of that will allow me to convert a 2 cosine A sine B into this, which is going to be here. So if I were to do this, let's try to write it down. So it's going to be equal to half of integration e to the power of cosine 2x. Then this will become sine A plus B. This is A, this is B. 3x plus x sine 4x. Oh, sine 4x. We have one here. Then after that, minus away sine A minus B. 3x minus x gives me 2x. So sine 2x dx. Sine 2x. We have it over here. Okay, so now we have the result that is from the previous part already. Let's try to expand this further. So this is going to be equal to this times this. So it is going to be equal to half integration of e to the power of cosine 2x times this sine 4x. Okay, and we know the result for this, it is going to be this. It is just integration of this. Then after that, this times this, it is going to give me okay. Let me just write it down first, okay, but I'm going to modify it a little bit. So we are supposed to have a plus half. Then after that, integration of e to the power of cosine 2x multiplied by this, which is going to be negative. Then after that, sine 2x dx. But if I were to make use of this result, I need a 2 over here. So I'm going to be factorizing out a 2. So if I'll be multiplying by a 2, so I need to add an additional multiplication of half outside. So this, okay, let me just write it down in the next row. So it will be half integration from e to the power of cosine 2x, then sine 4x plus half times half, it is going to be 1/4. This will help me to introduce a negative 2. Okay, that's what I want. This will help me to introduce a 2 into this. It will be 2, then e to the power of cosine 2x sine 2x dx. Okay, now we have results that I can make use of based on just what we have gotten in the previous 2 parts. So for this, it is going to be equal to half of this, which is going to be this. So half of e to the power of cosine 2x, 1 minus cosine 2x plus 1/4 of the result is going to be e to the power of cosine 2x. Let's not forget about the plus c. I can leave my answer here, or if you really want to, you can also try to factorize out e to the power of cosine x, and that will give you e to the power of cosine, factorize out e to the power of cosine 2x, and that will leave you with a 3/4 minus 1/2 cosine 2x within the bracket. So I have this plus c. Next, let's take a look at question 5. Okay, we have already finished this question number 4 so far, okay? Let's take a look at question number 5. Question number 5 gives us a diagram that is like this, and we are supposed to show that AC here is equal to this. Let me erase the board first. So in this question number 5, we are supposed to prove that AC is equal to that expression over there. We are going to be given just 2 marks, so I'm not expecting the solution to be that long. So in order for me to prove the AC is equal to this, I'm going to break up AC into 2 parts, AB, then after that BC. And if you were to look at AB, and if I were to just draw a vertical line up, I will be getting a right-angled triangle over here. Okay, let me just do a quick sketch of this right-angled triangle. It is going to be this. AB is here. Okay, A is here, B is here. This is the right-angled triangle that I'm talking about. And since this length here is 2, this tells me that this will be 2. This angle here is given to me, this angle here is given to me as pi over 4 plus theta. So based on this, we can apply what we have learned in our trigonometry. I'm going to make use of sine. And I know that sine of this angle, pi over 4 plus theta, this is going to be opposite over the hypotenuse, which is AB. This tells me that AB is going to be equal to 2 over sine of pi over 4 plus theta. I'm going to work on another triangle which takes into account of BC. So the triangle that I'm going to go for is this triangle over here. Let me do a sketch of this triangle. So it will be this. It is going to be another right-angled triangle. And this is where B is, this is where C is. This length here is given to us as 2. That will synchronize to this that is here. This angle here is going to be the same as this angle pi over 4 plus theta. So here we have a pi over 4 plus theta, which means that if we were to do a cosine of pi over 4 plus theta, this is going to be equal to the adjacent over the hypotenuse, BC, which means that BC is equal to 2 over cosine of pi over 4 plus theta. And this gives me AC, because AC is going to be AB plus BC. AB is 2 over sine of pi over 4 plus theta, plus BC, which is going to be 2 over cosine of pi over 4 plus theta. And we are supposed to write it in the way that the question wants, which is just simply factorizing out 2 from here, right? So it's going to be just 2 of 1 over sine of pi over 4 plus theta, then plus 1 over cosine of pi over 4 plus theta. Okay, this is what the question wants us to show. Next, hence, the question says, we are supposed to show that AC is going to be this quadratic polynomial over here, where R and S are constants to be determined. So we are attempting to re-express this into a polynomial, and to do that, we are going to make use of Maclaurin's. Because the purpose of Maclaurin's that we are learning in our H2 math is to convert any expression into polynomials. So we're converting this expression into polynomials. So let me rewrite this that we have here, and the question actually gave me one more piece of information, which is the fact that we are working on a theta that is sufficiently small. What is sufficiently small? the question didn't define for me directly, but it did give me an information about small indirectly, which is this that we have here. Because AC is approximately this, and it ended up at theta squared, which means that theta to the power of 3 and above, they are small enough to be negligible. Okay, so I'm going to take that into account at the same time as I try to do a Maclaurin's expansion for this. I'm not going to expand it first, but what I'm going to do is I'm going to just re-express the denominator by making use of trigonometric identity again. I'm going to make use of this identity here. Okay, the first two, I'm going to be making use of this. So AC is going to be 2 times of 1 over this, which I'm going to make use of the first identity, which will give me a sine pi over 4 cosine theta plus cosine pi over 4 sine theta. Then plus, for the second one, I'm going to be making use of the second identity, which is this one over here. This tells me that cosine A plus B is going to be cosine A cosine B minus sine A sine B. So we have a cosine pi over 4 cosine theta minus sine pi over 4 multiplied by sine theta. So here we have a sine theta. So it will be 1 over this. Let's go back to the question. It is supposed to become a linear format. And we can see and evaluate this sine pi over 4 cosine pi over 4, because we can see that it is going to become the same thing, which is, what is it? 1 over square root of 2. This will also become 1 over square root of 2. This will also become 1 over square root of 2. This is also 1 over square root of 2. So we can sort of like factorize it out. Okay, so this will become 2 times of factorizing this out. It will give us a 1 over square root of 2, which is going to be equal to square root of 2, divided by this, which is going to be cosine theta plus sine theta. The same goes for this. If I were to factorize out, it is going to become square root of 2. Okay, 1 over square root of 2 is going to be square root of 2. Over, we're going to be left with cosine theta minus sine theta. And let's factorize out square root of 2 also. And that will be giving me a 2 square root of 2 of 1 over cosine theta plus sine theta. And this will be 1 over cosine theta minus sine theta. And the next thing that I'm going to try do is to start to do some approximation making use of Maclaurin's. I'm going to go back to my MF26 into my formula sheet again. And this time I'm going to go to the Maclaurin's portion of my formula sheet. And specifically, I'm going to be making use of the sine and cosine result. And ignoring anything that is theta to the power of 3 and above, like what we have deduced just now about theta being small enough. So this is going to be equal to 2 square root of 2 of cosine theta. We have this. Okay, it will be cosine theta will be 1 minus theta squared over 2 factorial plus theta to the power of 4. I'm going to be ignoring it. So I'm going to be just keeping the first two expressions. So this will be 1 over cosine. This cosine over here, I'll be converting it to 1 minus theta squared over 2. Then plus sine theta. Sine theta is going to be this. Sine theta is going to be theta minus theta over 3 divided by 3 factorial. Theta over 3, I'm going to be ignoring it because it is supposed to be small enough to be negligible. So sine theta over here will just become plus theta. Then plus 1 over cosine theta, the same thing, 1 minus theta squared over 2. Then after that, minus theta. And since we are doing an approximation, I'm going to just change this, okay, just to make sure that I'm indicating the fact that I've already introduced an approximation is this, and this is just polynomials in the denominator. But we don't want polynomials in the denominator. We want the polynomials to be existing only in the numerator so that we can prove what the question wants me to prove. So I'm going to bring the denominator up. So I'll be rewriting this as 2 square root of 2. Bringing this up, it will become 1 minus theta square over 2 plus theta to the power of minus 1. And because I will be regrouping this in a short while, and I think I'm going to just rearrange this. Okay, so it looks nicer, it looks more similar to the way that we usually write polynomial in, which is going to be either in ascending powers or in descending powers, and this is like in a mess. Okay, so I'm going to rewrite this so that it is in ascending powers. So what we have here is going to become a plus theta minus theta square over 2 to the power of minus 1. Okay, it is just bringing this entire expression to the numerator. I will do the same thing for this, and I'm also going to rearrange this so that it is going to be in ascending powers. So plus 1, then minus theta square over 2 to the power of minus 1. And the next thing that I'm going to do is I'm going to go back to my MF26 again, and this time I'm going to make use of this other expansion that is given to me, which is this 1 plus x to the power of n, because we have a version here. Can you see the 1 plus x to the power of n in here? If you cannot see, that is because you have yet to regroup the terms together. If I were to regroup the terms together, this is n definitely, it is 1 definitely. So this over here, I'm going to group it as one term by itself. So it will become this. So this, okay, this will become one term. I'll do likewise for this. I will regroup this entire expression here, these two terms here, into one single term, so they can become 1 plus a variable to the power of n. So I'm going to regroup this. Let me rewrite. So if I were to regroup this, it is going to become plus, then we will have a minus, we will have a minus theta over 2. Okay, then this bracket, let me just change it into a square bracket. Maybe if I were to just be very, very precise in my presentation, I'm going to use another bracket to represent this. So we have another form. The other form looks like this, and now we are ready to do an expansion based on this second formula that is inside our MF26, inside our formula sheet. So it will be 2 square root of 2. Let's expand this, okay? So using what we have here, it is going to be 1 plus n, which is minus 1, then x, which is going to be theta minus theta square over 2. And the next one is going to be, according to what we have, is going to be minus 1, which is minus 2, divided by 2 factorial, then theta minus theta square over 2 square, and so on. This will be for this in the expanded form based on what we have in our MF26. As for this, it is going to be plus 1 plus minus 1 minus theta square over 2 plus minus 1 minus 2 divided by 2 factorial minus theta square over 2 square, and so on. Okay, we have this. Let's simplify this. It is going to be 2 square root of 2, and we will have a 1 minus theta plus theta square over 2. Minus 1 times minus 2 is going to be 2. 2 divided by 2 is going to be equal to 1. And if I were to expand this, there's only one term that I'm going to be keeping, which is the very first one. Because if I were to be expanding this, the first one is going to be theta square. Theta square is what I'm going to be keeping. The next one is going to be theta to the power of 3, which is what I'm going to be neglecting. So I will have this. Okay, the rest of the terms I'm going to be neglecting them. For this, it is going to be a 1 plus theta, then plus another theta square over 2. As for this, this will become 1. This the same as how it is functioning here. If I were to take the first term square, it's going to be theta square. The second term is going to be theta to the power of 3. I'm going to be ignoring theta to the power of 3. So I'm going to be left with a plus theta square. Sorry, this is theta square. Wait, this is the expanded version of this. I wrote it wrongly. So theta square is going to get me here. This will give me a theta square, which will get me here. I'm ignoring the next term. I'm ignoring the next term because the next terms in these two expansion is going to be theta to the power of 3, which is negligible. So we have this plus dot dot dot. and this will be equal to 2 square root of 2. Let's try to sum the terms together, okay? So 1 plus 1 is going to give me a 2, minus theta plus theta, theta will disappear, and this plus this plus this plus this gives me a 3 theta square, and the rest of the terms, I'm going to be ignoring them because it's going to be theta to the power 3 and above. And if I were to expand this further and ignoring this, let me put another approximation notation. This times this is going to be equal to 4 square root of 2. This times this is going to be plus 6 square root of 2 theta square. And this gets me the format that the question wants me to show. Let's take a look at the question again before we forget about it. So that gives me the format that the question wants me to show, and the question also requires me to quote and determine the values of R and S. So R is going to be this. Therefore, R is equal to 4 square root of 2. And S is the coefficient of theta square. So S is going to be equal to 6 square root of 2. This is for question number 5. Let's do another one. Let's take a look at question number 6, which is this over here. Another integration question together with this kind of rectangle question, which is a bit of summation that is going on. Okay, in this question number 6, part 1, we are supposed to be using a substitution that is given to us to help us to integrate the integral that is also given to us. The integral is this. Integration from 0 to 1 of 1 over square root of 1 plus x squared. Okay, we are supposed to be integrating this with the help of this. So we're going to be trying to replace all the x by tangent theta. So this x will be replaced by tangent theta. We are going to be trying to replace this also. To do that, we will go for dx d theta, which is going to be equal to secant square theta. And we also need to replace these two x. This is when x is equal to 0 and x is equal to 1. So when x is equal to 0, that will mean tangent theta is equal to 0. So theta is going to be equal to 0. And when x is equal to 1, this will mean that tangent theta is going to be equal to 1, which means that theta is going to be equal to pi over 4. So this can now be rewritten. 0 is going to be replaced by 0, and 1 is going to be replaced by pi over 4. And this is 1 over square root of 1 plus x squared, which is going to be tangent square theta. Dx is going to be replaced by secant square theta d theta. So this is going to be integration from 0 to pi over 4 of 1 over square root of 1 plus tangent square theta is secant square theta. Then secant square theta over here, d theta. This is going to be from 0 to pi over 4 of 1 over this. This is secant theta. And here we have a secant square theta d theta. And we will be ending up with from 0 to pi over 4 of secant theta d theta. And to integrate this, we have a result that is from our formula sheet. Again, let us take a look at it. So in our formula sheet, let's go to the integration portion. Yep, it is here. So we can see that integrating secant x is going to be equal to ln secant x tangent plus tangent x. So this is going to be, if I were to integrate this, okay, I should have already integrated this since I'm using the result that is from there. So this will be ln of secant theta tangent theta. From 0 to pi over 4, let's substitute the numbers in. It is going to be ln of secant pi over 4 plus tangent pi over 4 minus ln of secant 0 tangent 0. So this will be ln of secant pi over 4 is square root of 2. And tangent pi over 4 is 1. So we have a modulus of this. In fact, we don't even need the modulus. Let me just rewrite it. So we have this minus away ln of secant 0 is 1. Tangent 0 is 0. So we have a ln of 1, which is 0. So my answer is going to be ln of square root of 2 plus 1. Oops, I should have removed this. So I have my result. Let me write my result here. I think it is going to be useful for the next part. So this is going to be equal to ln of square root of 2 plus 1. Let me erase this so that we can proceed to the next part of the question, which require us to refer to the graph that is given to us. So in part 2, we are now given a graph. Let me just very quickly do a quick sketch of the graph. So we have this over here, and the graph is something that is like this. Okay, this is the graph of y is equal to 1 over square root of 1 plus x squared, having the same expression as this. So for this graph, it is going to be, we are going to be working on the regions of x, that is from 0 to 1, that is given to us by the question. And rectangles are going to be drawn below the graph in this way, where the width is 1 over n, which means that we're going to be drawing, because we are looking at from 0 to 1. So if the width is 1 over n, we are going to be drawing n numbers of rectangles. So let me go from 0 to 1 here first. Okay, so let's say this 0, let's say 1 is all the way here. This is 1. So we are supposed to show that the area of all the rectangles that are shown here is given to us according to that series that is given. So area. Okay, let's start. Area is going to be sum of all the rectangles, right? So it's going to be base times height. What is the base of the first rectangle? Let me just sketch that first rectangle. The base length of the first rectangle is 1 over n. How about the height of the first rectangle? We can see visually the height of the first rectangle is this. And the height is going to be in accordance to the y coordinate of this point here, right? How do I get the y coordinate of that point there? I will just do a substitution. So the height is going to be equal to 1 over square root of 1 plus x, which is 1 over n squared. Then the second rectangle. The second rectangle is going to be here. This is going to be 2 over n, obviously, right? Because the width, according to what the question says, the width of all the rectangles, they are 1 over n. So this must be plus another 1 over n, which will give me an x coordinate of 2 over n. And the height of the second rectangle is going to be defined by the y coordinate of this point, which is substituting the x coordinate 2 over n into this. So let us write down the area of the second rectangle. The width is 1 over n again. As for the height, it's going to be substituting this x coordinate into here to get the corresponding y coordinate. It is going to be 1 over square root of 1 plus x squared, so 2 over n squared. Then plus, the same goes for the third one. The third one is going to be somewhere here. Okay, plus another 1 over n, this is 3 over n. And the height is going to be determined by the y coordinate of that particular point. The width is 1 over n, and the height is going to be the y coordinate. So substituting 3 over n into here, 1 plus 3 over n square. And we are going to write all the way until the second last rectangle. The second last rectangle requires me to draw the last rectangle. So let me just go for this and one more vertical line that is here. So this is the second last rectangle. For the second last rectangle, the width is still going to be equal to 1 over n. And the x coordinate is going to be this x coordinate that is here. It is 1 minus 1 over n. 1 minus 1 over n is equal to, actually the question has already given us the x coordinate of this, which is n minus 1 over n. So the height is when I substitute x into, I substitute n minus 1 over n into this x over here. So for the second last rectangle, the width is still going to be 1 over n according to what the question says. And this is 1 over square root of 1 plus x, which is going to be replaced by this, n minus 1 over n squared. Plus the last rectangle, we will also know that for the last rectangle, the width is 1 over n and the height is this height over here, where the y coordinate represents the height, the x coordinate is equal to 1. So it's going to be 1 over square root of 1 plus 1 squared, because the x coordinate now is going to be equal to 1. Let's simplify this, and hopefully we are going to be getting this series that the question is trying to ask us to get. So this 1 over n, I think I can actually push it into the square root by rewriting n. I'm going to be rewriting this n over here as square root of n square. So we have sort of like a 1 over square root of n square. So square root, this square root, this n square, I can bring it into the square root, which will give me a 1 over square root of n square. Then we will be multiplying this by a 1 plus 1 over n square. Okay, because according to what the question wants us to show, there's no 1 over n outside. It is just going to be a square root in the denominator. I think this is fine. Okay, maybe I will just use the curved bracket instead. It's not very necessary for me to use the rectangular bracket. I will do the same thing for this. Rewriting this into this form allows me to bring it into the square root. That will be 1 over square root of n square multiplied by 1 plus 2 square over n square. I'm maintaining the 2 square instead of rewriting it as 4 because the question also wrote a 2 square, subsequently 3 square, and so on. So this will be plus this. Again, I'm going to do the same manipulation, rewriting this as n square multiplied by 1 plus 3 square over n square, all the way until this, which is going to be 1 over square root of n square, and 1 plus n minus 1 square over n square, plus this will be 1 over square root of n square of this is actually just going to be square root of 2. Oh, that's just going to be 2. I've already written the square root, so let me rewrite this. So this will be 1 over, and I'm going to bring it inside. It is going to be n here, n square here. This 1 plus 1 is going to be equal to 2. So we have this, which is, I think the next step can already, we can already write it in accordance to what the question wants me to show, because multiplying n square into the bracket here is giving me n square plus 1. Then after that, this multiply in is giving me n square plus 2 square. Then we will have n square plus 3 square all the way until this, which is n square plus n minus 1 square. And finally, this is square root of 2n square. Is this 2n square that the question wants me to prove? Yep, 2n square. So this is what the question wants me to show. And the very last part, we are supposed to be talking about the limit of a when n tends to infinity. What will happen when n tends to infinity? When n tends to infinity, when n tends to infinity, a will become a, which is the sum of all this, okay, sum of all the rectangles. So when n tends to infinity, 1 over n, which is actually the width of all the rectangles, will become smaller and smaller and smaller and smaller, which means that the approximation will get better and better and better, because for the same width, 0 to 1, we are going to be dividing into even more rectangles, which are going to be underestimating this area, but it will just get so much when n tends to infinity that a will tend to the exact area. It will tend to the exact area under the graph. And what is the exact area under the graph? The exact area under the graph is going to be integrating from 0 to 1 of 1 over this, which is going to be square root of 1 plus x squared. And what is our answer going to be? The limit of a when n tends to infinity will become ln of square root of 2 plus 1. So this is going to be the answer to the last part of this question. Let's do one more question, then I'm going to leave the rest of the paper to be done in the next video, okay? One more, which is this question number 7 here. Let's check it out. So for this question, question number 7, we are given a sequence of positive numbers, u1, u2, u3, which is going to be following a strictly increasing arithmetic progression. So as it gets from u1 to u2, it gets bigger, u3 is going to be bigger than u2, and so on. It is given that the first term is a and the ninth term is b. In part 1, we are supposed to find u3 in terms of a and b, and show that u3 u plus u5 plus u7 is equal to that expression over there. So in part 1, the question tells me that u9 is equal to b. I'm going to assume that the common difference for this arithmetic progression is d. That means that the first term, a plus 9 minus 1, which is 8 times of d, this is equal to b. This tells me that d is going to be equal to b minus a over 8. Okay, d is going to be equal to this. So I'm going to try to find u3 in terms of a and b. u3 is going to be equal to a plus 3 minus 1, which is 2 times of d, which is going to be a plus 2 times of b minus a over 8. So u3 is going to be equal to 3 over 4a plus 1 over 4b. u3 is this. And we're supposed to find what is u3 plus u5 plus u7. Of course, we can make use of the sum of AP formula, or maybe it is even faster if we can just find u5, then after that use u7. Because what is u5? u5 is just simply going to be u3 plus d, right? u3 plus d is going to give me u4 plus another d is going to be giving me u5. So I'm going to take u3, which is 3 over 4a plus 1 over 4b plus d, which is plus 2d. So this is going to be 3 over 4a plus 1 over 4b plus 2 times of b minus a over 8. And this will give me u5. Let me just write it down here. This will give me u5. If I were to simplify it, u5 is going to be equal to 1 over 2a plus 1 over 2b. Then u7 is going to be equal to u5, which is this 1 over 2a plus 1 over 2b plus d. u5 plus d is going to give me u6. u6 plus another d is going to give me u7. So it's going to be 2 times of d that is here. It's going to be 1/4 a plus 1 over 2b plus 2 times of b minus a over 8. Simplifying this to get the u7, it is 1/4 a plus 3/4 b. So what is u3 plus u5 plus u7? It is going to be equal to this 3 over 4a plus 1 over 4b, this is u3, plus u5, which is 1 over 2a plus 1 over 2b, plus u7, which is 1 over 4a plus 3 over 4b. This will simplify to 3 over 2a plus 3 over 2b, and if I were to factorize this, rewriting this as b plus a instead, we will be able to show what the question wants us to show. So this is it. And for part 2, let's see. For part 2, given that a, u3, and b, they are consecutive terms of a geometric progression. So u3, a, u3, b, they are consecutive terms. So which means that u3 divided by a is going to give us a common ratio, which is going to be the same as b divided by u3. Okay, because they are consecutive terms of the geometric progression. So with this, we know that u3 square is going to be equal to ab. This is the first piece of information that I have. And we are supposed to express b in terms of a using this piece of information that we have. What other information do we have? Because I don't think this is possible for us to just immediately express everything in terms of, oh, maybe it is possible. Okay, let's try to work it out first, because we do have u3's expression, right? Because u3 is from here. Okay, so I will be able to get an equation that is in terms of a and b. Let's see whether this will work, because I'm supposed to be just expressing b in terms of a. So once I get the equation, it's just going to be in terms of b and a. Okay, let's try. So u3 is going to be equal to this. So I'm going to take 3 over 4a plus 1 over 4b square. This is equal to ab. Okay, since we have no other information that is given to us already. So we have this. Expanding this gives us a 9 over 16a square plus 2 times of this times this. This gives me a 3 over 8ab plus this square 1 over 16b squared. This is equal to ab. If I were to bring ab over to the left-hand side, I will have a 9 over 16a squared minus 5 over 8ab plus 1 over 16b squared. This is equal to 0. I'm going to multiply this throughout by 16. Okay, so it is easier for me to look at the expression that we have on the left-hand side. That will give me a 9a squared minus 10ab plus b squared. This is equal to 0. We can factorize this. If I were to factorize this, I will be getting a 9a minus b, a minus b. This is equal to 0, which means that 9a minus b, this must be equal to 0. This tells me that b is equal to 9a. Or another possibility is a minus b is equal to 0. This tells me that a is equal to b. And this is not possible. Why is this not possible? This is not possible because b is actually the 9th term. And a is the first term. And according to what the question says, this is an increasing arithmetic progression. Okay, we're expecting the 9th term to be bigger than the first term. Okay, so they cannot be equal. This is not possible. So my answer is going to be this. Okay, I guess this is enough for me to work on the question. Okay, b is equal to 9a. This is part 2. Hence, determine if the sequence consisting of consecutive terms ln u3, ln u5, and ln u7 is an arithmetic progression. Okay, we are going to make use of this information. Let me write it down here, part 2. Part 2, we determine that b is equal to 9a, okay? Let's try to work on part 3, where we are given 3 consecutive terms. And the 3 consecutive terms, we are supposed to prove that they are belonging to an arithmetic progression. So for part 3, the 3 consecutive terms, let me just write it down first. They are ln of u3, the first term. Then the next term is ln of u5. And then we have a ln of u7. If they are to be consecutive terms of an arithmetic progression, then we will be expecting ln of u5 minus ln of u3 to be the same value as ln of ln of u7 minus ln of u5. Okay, so let's check whether this is true, because if this is true, okay, if I'm getting the same number, same result, then we will be expecting, then we can conclude that we are looking at an AP. So let's see. This is equal to ln of u5 over u3. And now I'm glad that we have used this, okay, because I have direct access to u5. So this is going to be ln of u5. This is half a plus half b divided by u3. u3 is 3/4 a plus 1/4 b. And then I'm going to use this. b is equal to 9a. So this is going to be equal to ln of 1 over 2a plus half times of 9. b is equal to 9a. So 9a divided by 3 over 4a plus 1/4 of 9a. All the a's can be cancelled. I am going to be getting this as ln of, this is going to be ln of 5 over 3. Okay, I'm getting a constant here. So let's see whether we're going to be getting the same constant when I do this. Okay, if it's so, then we are looking at an AP with a common difference of ln 5 over 3. So this is equal to ln of u7 divided by u5. So it is going to be ln of u7 is 1/4 a plus 3/4 b divided by u5, which is going to be half a plus half b. And this is ln of half a plus 3 over 4b, which is 9a. We have found this in part 2, divided by half a plus half b, which is also 9a, which we have found out in part 2. And this gives us a ln of 7 over 5, and it is not equal to ln of 5 over 3. Therefore, this is not an arithmetic progression.